Welcome to this discussion on multi-cad design reuse, as it is supported by the Teamcenter SolidWorks integration. Let's begin by defining what is meant by multi-cad design reuse. In general, it means designing your SolidWorks assembly around, and in some cases against, designs authored in other CAD software. It can be subdivided into three modes, or categories. Direct reuse means the non-native models are never converted to SolidWorks models. They are just reused as is, in the SolidWorks session. Direct reuse is possible for Creo, Inventor, Solid Edge, and depending upon configuration, CAD. Indirect reuse means first converting the non-native models into a neutral format, such as JT or STEP, then importing them into SolidWorks. Finally, hybrid reuse involves directly reusing the non-native models, but only at the part level. The non-native assemblies are constructed on the fly, by the Teamcenter SolidWorks integration, as they are opened. This category applies to NX, and in some cases, CAD. Direct reuse is possible anytime SolidWorks can directly open the non-native models through its 3D interconnect technology, first introduced in SolidWorks 2017. A key benefit of direct reuse is that the Creo designer can use the non-native models as if they were native. He can establish parametric constraints to them, and as the non-native designs are changed in their authoring tools, and saved to Teamcenter, the SolidWorks design will adapt. An important consideration, and potential drawback, of direct reuse is that it requires careful management of the version dependencies between SolidWorks and other MCAD software. The SolidWorks version must be new enough to open files from the other CAD tools. Indirect reuse is the more traditional data exchange technique, in which a neutral file is exported from the CAD session, then imported into SolidWorks. Common examples are STEP and JT. In the managed Teamcenter environment, it has several limitations, as noted here. Unlike direct reuse, indirect reuse cannot provide parametric associativity. Any CAD-level constraints attached to non-native models will be lost the next time the SolidWorks assembly is opened. On the plus side, version compatibility is usually not an issue with indirect reuse, precisely because the exchange format is neutral to both the authoring and the reusing CAD software. The third and final reuse category is hybrid. It is not yet supported by the Teamcenter SolidWorks integration, but can be evaluated by adding undocumented settings, which will be explained here. It's based on the long-standing technique used by other integrations for JT-based assembly reuse, which is to download the part JT files, then build the non-native assemblies on the fly, as the JTs are being imported into SolidWorks. In the hybrid case, the non-native CAD parts are downloaded, and their assemblies are dynamically built by the integration, using the positional information from the Teamcenter BOM view revisions. The goal is to retain some degree of associativity, as long as constraints are made against only the parts, and not the assemblies. This technique is appropriate in cases where the non-native assemblies cannot be opened from Teamcenter without the involvement of their Teamcenter integrations. This is always the case with NX. Several rules are observed by the Teamcenter SolidWorks integration, when working with non-native design data. First, if a native SolidWorks model is found, it will always be used. Any other MCAD file, even if configured for reuse, will be ignored. Non-native models that are opened or inserted from Teamcenter cannot be saved back to Teamcenter as SolidWorks models. This preserves their identity and avoids duplication of designs under different CAD formats. Finally, nested reuse cannot be supported. Non-native assemblies of any depth may be inserted into SolidWorks parent assemblies, but they themselves must not contain any non-native children. Several configuration settings serve to tell the SolidWorks integration which non-native formats may be used as components. Two sets of preferences in swim.properties specify the types of datasets, and the named references within those datasets, that are eligible for reuse. Please note that all type names must appear in the swim.properties file exactly as they are defined in the appropriate BMIDE template, including case. For each dataset type mentioned in the swim.properties file, up to 3 entries are required in the BOM map section of the swim.xml file. These entries specify which non-native types may be used by SolidWorks assemblies, as well as which non-native part datasets may be used by non-native assemblies. Here we see a Creo example. Unlike the swim.properties preferences, all dataset type names used in the BOM map must be entirely lowercase. Now let's look at some examples of direct, indirect, and hybrid multi-cad design reuse. First, we'll directly insert a Creo and an Inventor subassembly into a SolidWorks design. Here we see the necessary settings in both the swim.properties and the swim.xml files. First, we must add the integration preferences. In swim.properties, both the data set types, and their named references, are specified. Next, in swim.xml, the BOM map is updated to tell the integration which data set types may be used as children of both native and non-native assemblies. Here, we see that there are 3 entries each for the Creo and the Inventor data set types. Now let's create a new SOLIDWORKS assembly, and begin directly adding non-native components from Teamcenter. Here is the new top-level SOLIDWORKS assembly being registered as a Teamcenter item, revision, and data set. Once created, we can begin adding sub-assemblies and parts to it, either from the local cache or from Teamcenter. In our demonstration, all components will be added from Teamcenter. First, we will find and add a Creo subassembly, using hosted active workspace search. Once found, the Creo design can be dragged and dropped. When it crosses the boundary between Teamcenter and SOLIDWORKS, a prompt appears, allowing the user to either open the design in its own window, or insert it into the active assembly. We will choose Insert. Again, due to SOLIDWORKS API limitations, a second drag and drop is needed to complete the insert. This is only the case for non-native design reuse. Native SOLIDWORKS assemblies do not trigger this additional prompt. Now we will find and insert a native SOLIDWORKS subassembly, to demonstrate how it can be positioned relative to the directly reused Creo design, with parametric constraints or mates. Later we will see how these constraints are maintained by SOLIDWORKS, when the Creo design is changed. In addition to the alignment mate, a dimensional offset is created between a surface on one of the Creo assembly components, and a surface in the native SOLIDWORKS design. Similar constraints can be established against indirectly reused models, but they will not be remembered by SOLIDWORKS the next time the assembly is opened. This is the main advantage of direct reuse over indirect reuse. We need a connector pin to join the linkage assembly to the landing gear. Knowing that the pin is available as an Inventor assembly, we find and insert it, using the same technique as was used for the Creo and the SOLIDWORKS sub-assemblies. However, something unexpected happens when the integration calls SOLIDWORKS to insert the non-native, directly reused design. A background session of Inventor is started, as can be seen in the taskbar. This is obviously undesirable and has been reported to SOLIDWORKS support. In the meantime, what can be done? The workaround for this type of problem is to fall back to indirect reuse, through the JT file format. This is easily done by replacing references to Inventor datasets and named references with direct model references, in the swim.properties and swim.xml files. Assembly-level reuse through JT is a special case for the integration. In addition to the general settings in swim.properties, 2 additional preferences are needed. The first allows the integration to build transient SOLIDWORKS parent assemblies using the JT, or other, parts. This setting is also needed for hybrid reuse, as we will see a bit later. The second preference is specific to JT and is needed due to certain implementation details. After logging out and back into Teamcenter, we can try once again to insert the Inventor assembly. This time, because of the configuration changes, the integration will find and use the JT part files instead of the native Inventor files. It will build a transient SOLIDWORKS assembly with the JT files, using positional information from the Inventor assembly's bill of materials. As can be seen, the Inventor assembly structure is replicated part by part, within SOLIDWORKS. This technique is also used to build NX assemblies for hybrid reuse. Once the subassembly is built, it can be positioned within the SOLIDWORKS design. It could also be mated, but any mates will be lost the next time the assembly is opened from Teamcenter. If nothing has changed, there is no problem because the positioning will still be correct. Before saving our partial design to Teamcenter, let's adjust the position of the SOLIDWORKS subassembly, using its constraint to the Creo subassembly. This will enhance the demonstration of what happens when the Creo design changes. Let's save our work to Teamcenter before continuing. The integration will not allow you to save the transient SOLIDWORKS assembly that was built for the Inventor JT parts, nor will it allow you to save the Creo subassembly or any of its children. Doing so would create duplicate SOLIDWORKS datasets under the Creo item revisions. What happens when the Creo design is changed, in its authoring tool, and saved back to Teamcenter? Remember that the Creo design is directly reused by SOLIDWORKS, allowing the SOLIDWORKS parent assembly to maintain any constraints that were made against the Creo models. In this case we're simply moving the feature that was used in the SOLIDWORKS mate. Back in SOLIDWORKS, a refresh is performed, and the integration informs us that something in the Creo assembly has been changed. Update model will download the new Creo file versions. Here we see they have been pre-selected by the integration, so all the user has to do is click Update. Due to an API limitation that has been reported to SOLIDWORKS, the user must perform the final step of the update, from within the SOLIDWORKS feature tree. Watch carefully, and you will see the SOLIDWORKS subassembly change its position to maintain its constraint to the Creo design. We will finish our SOLIDWORKS design by adding an NX subassembly. Because the NX assembly is managed in Teamcenter, it cannot be opened simply by downloading all of its files. Instead, the integration will open it in hybrid mode, by downloading the part files, and building the NX assembly on the fly. This is similar to JT-based reuse, but it enables part-level associative design, meaning that SOLIDWORKS assembly constraints can be established against the NX parts. In addition to NX, we will add a step file that could have been exported from any mechanical design tool. These are the required preferences that must be added to swim.properties and swim.xml. You will notice that, because we're reusing NX in hybrid mode, an additional tag appears in its BOM map entry. The swim.properties file has been updated with preferences for UG master and step datasets, and their named references. The preference that enables hybrid reuse is retained. In swim.xml, only one entry is required for the step dataset type, because it has no structure. Only two entries are required for the UG master type, because it also does not contribute structure to the assembly that is built in SOLIDWORKS. That is the purpose of the assembly equals ignore tag. It tells the integration to ignore NX assemblies and only download the parts. Our landing gear assembly needs an axle, and the axle is available in Teamcenter as a step data set. The integration recognizes and handles it like any other non-native part. Now we have an axle upon which to mount the NX wheel assembly. As with JT, the integration will download the NX parts, and use them to build a transient SOLIDWORKS assembly. The only real difference between JT and hybrid reuse is that with hybrid reuse, there is the possibility to create and retain constraints to the non-native part models, whereas with JT, this is not an option. Once the NX subassembly is positioned, our SOLIDWORKS landing gear assembly is complete and ready to save to Teamcenter. From top to bottom, we have a top-level SOLIDWORKS assembly, a hybrid NX subassembly, an indirectly used, through JT, inventor subassembly, an indirectly reused step file, a directly reused Creo subassembly and a native SOLIDWORKS subassembly. Only the native SOLIDWORKS models may be saved to Teamcenter. When the save is complete, we can see the entire multi-cad bill of materials in Teamcenter, matching what was done in SolidWorks. Of course, when the SolidWorks assembly is reopened, any changes made to the non-native designs will appear in SolidWorks. We hope you have enjoyed and learned from this overview of the multi-cad mechanical design reuse support provided by the SolidWorks integration. As you have seen, there are several different options for reuse of non-native design data in SolidWorks, under Teamcenter management.